Good afternoon. I would like to start today's lecture series. And today's speaker is Dr. TaeyongLee from Ewha Women's University. And I'd like to introduce my colleague and my friend, Dr. TaeyongLee. And he received his PhD degree from biomedical engineering, in biomedical engineering from the University of Wisconsin at Madison in 2001. Then he moved to Harvard, and he also joined Johns Hopkins as a research associate and postdoctoral fellow. And he moved to Singapore, National University of Singapore, as an assistant professor, and he stayed there for 10 years. And a few years ago, he moved back to Korea, and now he's an associate professor of Division of Mechanical and Biomedical Engineering at Ewha Women's University. And please welcome Dr. TaeyongLee. And today's presentation title is Engineering Approaches of Medical Images.
Thank you very much for your introduction. Good afternoon, everyone. I am TaeyongLee from Ewha Women's University. I'm going to talk about the engineering approaches of medical images. In the abstract, I only gave the numerical analysis, but for the comparison of our numerical analysis and the experimental data, slightly changed the title, subtitle to numerical and experimental analysis. Before I begin, let me give you the overall idea. So what am I trying to do? It's basically, I want to get some material properties or engineering properties out of images. You know, we can always think that the image is a simply image. But nowadays, we are in the 21st modern technology period, then we can always get the lots of information, especially in the clinical side, or from more in detail, the medical images, we can get some properties. So let me start from the natural aging that each and every of us is experiencing. So the left one is the young femur, and right one is the old femur. If you look at the outside of the femur, you cannot differentiate the differences. But if you see inside of it, the outside of the bone is called the cortical bone. Inside network structure is called the trabecular bone. There are not much differences in the cortical bone, but there are lots and lots of changes happens in trabecular bone. Good example is that trabecular bone itself disappears. That's why you can see this big hole. So if you look at the cross-section of this femoral neck, this is a schematic diagram. As you can see in here, in the young bone, the black like donut is the cortical, inside is the trabecular. So starting from, let's say, female, male, x-axis is age 20s to 100 years old. So if you look at the cross-section of your femoral neck, female, male, so this is how it looks. As we are getting older, it is true that the cross-section diameter of this femoral neck is increasing. At the same time, the thickness of this cortical bone is decreasing. So one thing, so that's the schematic diagram showing that the diameter as compared to 20s to 100, diameter is increasing. But if you look at it here, the thickness of these donuts is decreasing. So if you are familiar with the bending moment of it, see that the relationship between the moment and the radius is actually in the R to the fourth in the circular cross-section. That's why a lot of people believe that as we are getting older, bone mineral density, bone density is decreasing. It is well known, but that doesn't really explain why elderly bones are more prone to fracture. And a good example is that the same BMI, same gender, like 80 years old and 20 years old, they slip. 80 years old subject has a higher chance of having fracture as compared to 20s. In the strength-wise, there is not much differences. We just have a belief that just because of bone mineral density is decreasing, the elderly bone is getting weaker. In some sense, yes, it's true, but if you understand the mechanics a little bit, it's not really true. So that's where the research rationale has started. So we want to understand, is it really true that the elderlies, our grandmothers or grandfathers, having a fracture just because they are getting old? In mechanics point of view, no, it's not true. So there must be something else. So you see, I mean, what is going to happen to this guy? 1 second later, right? So if you look at, I mean, this is schematic diagram, he's going to fall down, right? So usually his hip, which is the greater trochanter, probably hit on the ground. So if you look at it here, right, his upper body weight going down, lower body weight going down, there's a ground reaction, the reaction force from the ground. Looks familiar, right? It's typical 3-point bending. So the superior region is on the compression, inferior is on the tension. Okay? So there are a lot of people who's been simulating our femur using this scenarios. And so some people, of course, use the finite element method. Some people use the finite strip method. You know, this is a simple version of a finite element method. So this is the simulation that we believe that people usually have a fracture on the femoral neck in this scenario. Then okay, let me talk about the osteoporosis. How do we diagnose the osteoporosis? We're relying on to the bone mineral density from DEXA machine. Okay? It's a dual energy X-ray absorption metric. So by using this machine, we can get the bone mineral density, I mean, in terms of the T-score in our spine and the femur. But as you can see in here, non-vertebral fracture for man and woman, you see the normal BMD about 18%, normal BMD of about 12%. The osteopenia is high risk of osteoporosis. According to WHO, osteopenia is not osteoporosis. So you're somewhere between normal and osteoporosis. But if you consider even this osteopenia, more than half of the normal subject or close to normal subject, they're exposed to fractures. So the gold standard of predicting or diagnosing osteoporotic fracture is actually wrong. In details, I mean, specificity, you know, I don't want to go in detail, but specificity, which if we leave the true negative as a fracture, then the accuracy has some problem. Means that if we tell a subject or patient that you will have a fracture, then it has a fracture. Or you will not have a fracture, then you're not going to have a fracture. So that's the accuracy. It's true positive and true negative. So accuracy is below 50%. So in the other word, we are not predicting fracture by using modern technologies. Good thing is that the WHO recognized the importance of predicting osteoporotic fracture. So they have a software called the FREX, you know, fracture risk assessment tool. So I got this only today, and this was announced in 2011 to worldwide. I mean, there are several countries, including in Japan. There's over 840,000 cases being used to predicting fracture. So I put all of these informations, and my chance of having fracture in the next 10 years is about 3.5%. So it is very simple. It's good in the sense that the WHO recognized the importance of predicting osteoporotic fracture. But at the same time, how can a simple software predicting individual fracture risk based on this simple, 12 questionnaires, including, body weight and your age and just a simple BMI or bone mineral density values? So in some sense, we believe that this is assaulting to engineers. We're in the 21st centuries, and then how a simple software, free software, we probably need just a 386 computer to run this software. Very simple. But is it really important? Is it really, can we trust on this software? Well, my personal opinion is that no, absolutely not. We cannot predict the fracture. So then, what can we rely on for predicting fractures? So here's the, so based on that background, we get the information or have a research question saying they're predicting fracture risk in elderly. And we have a subtitle called Beyond Bone Mineral Density. Okay? Well, as I said, I mean, no one parameter can characterize the hip fracture, as we already know. And etiology is a multifunctional, multifactorial. So this is a little bit of conclusion in advance, but you see that the bone mineral density, which is available now, plus geometry, which I will explain to you later, and the bone strength. Okay? All of these three, we have to combine together to predict the hip fracture risk. So together with the Yonsei University, when I was in Singapore, we had the 107 subject, and we analyzed as I said, those three factors. So bone mineral density from the DEXA machine, and all of this, we have a CT scan, which we can get the information of geometric analysis as well as the structural analysis by using finite element analysis. So we have a triaxial representation of each subject, of about 107 subjects. So we have 107 subjects, we analyze all of these three factors together. And then we push a little bit further that because this subject, they have the record of 3 years. So not just get the information of each subject on specific point, but we follow those subjects over 3 years and see that which drug is really make our bones stronger, not just BMD. So these subjects, some control subjects, they don't take medicine. Some subjects, they take I'll explain later, but they take the bisphosphonate, which is anti-resorptive drugs. Another one is the anabolic treatment, which is a parathyroid hormone. So two different types of drugs and control, we want to see the efficacy of those drugs. Is it really working or not? So geometric analysis, what we did is that from the CT scan of the one femur, so we generate this 3D model, and then we cut the cross-section, image-wise cross-section, and we get the narrowest neck of the cross-sectional area, right? So if we cut it in here, and if you look at it this way, then you see this donut shape, narrow neck slices. Okay? Then each of these profile rays, so let's say this one is a 0 degree, 0, 30, 90, 0, 30, 60, 90, and then like this. So we analyze the radius and the thickness. So if you look at here in the 180 degrees, right, from the center to hit the cortical bone, this is the Hounsfield unit, which is how much bone is located. So from here to here, trabecular bone. When we hit on this cortical bone, this is amplification, right? It means that there is a bone. And then outside from here to here, there's no bone. Okay? So if I realign this from the center to outside, center to, this is a peak, outside. So from here, what we can get is simply, this is what we call the Berkering ratio. Nothing but the radius, mean radius over cortical thickness. So R over thickness, radius over thickness. I know this is very crude, a very simple way of predicting fracture. But hope you remember the first slide. As we are getting older, cortical thickness is getting smaller, while the radius is getting bigger. Okay? So this is we call the geometric analysis from the CT scan. So this femoral neck, proximal femur on the cross section, 107 subject in 2008, 2009, 2010. So we have over 300 analysis. So we are following each subject. Some of you already know that the finite element method, So this is the 5.1 millimeter cube of trabecular bone. So we can, there's some, I'm not going to go into the details, but you have the certain number. You just cut this into the certain number, finite number, right? Finite element. Let's say 1 million or 5 million, right? And then we do the analysis. We can do the different boundary condition. For example, we can confine in this edge, or we let this edge as the unconfined so that is movable. So there are some techniques get involved on this, so we can get the structural analysis. So with the boundary condition, as I said, the person who's about to fall, right? So it's like a 10-degree fall on the greater trochanter. This is called the greater trochanter. So we have the upper body pressure going down, and this one is the fixed. And if you look at the, it should work then. As you see that this is a superior region in the compression. This side is a compression, and the inferior region is on the tension. So this is geometric and structural analysis. So we are trying to combine those two with the one subject. So this is geometric analysis, 2008 and 2010. So you see that the geometry, I mean, there are some certain areas, 2008, 2009, 2010, there isn't any differences. So we call this as a profile rate, 0 degree, 30 degree, 60 degrees, and this is, in some sense, it makes sense that our bone doesn't change a lot. It's not noticeable difference in 3 years, right? And also, they are usually elderlies, Their changes, bone remodeling rate is not that high. But we can do the numerical analysis. This probably, you see that the high bone mineral stress has disappeared. Maybe this is because of the medicine. Or we can do some similar, same thing. This is a geometric analysis, and this is a structural analysis. So basically, now we have the material properties, structural analysis, and geometrical analysis. Remember the triaxial analysis. So we want to predict the fracture risk of elderly femur in terms of material property, which is how much hydroxyapatite located in our bone by using bone mineral densities. And also structural analysis. We have some boundary conditions, finite element method. And the other one is the simple geometry. We just look at the femoral neck because the fractures usually happen on the femoral neck. So these are most complicated. This is something available from the hospital right away. Even military bases, they have the bone mineral density, the DEXA machine these days, very popular. And geometry is very simple. We make a simple code, and we can see the boundaries very clearly. So these three approaches, and we combine those three together as compared to the current gold standard of looking at bone mineral density only. So one parameter versus including those three parameters. So that's what we are trying to do. So at the beginning, this complicated curve. So we look at it in the y-axis. Y-axis is, I believe, bone mineral density. No, this is the Berkman ratio. No, this is a Berkman ratio. This is BMD, and I think this is a critical fracture load. 2008, 2009, 2010 is difficult to chase. See that? Some increment in the z-axis, minus 10.9% and 0.5% increment. The same story. So we really had a hard time to understand this curve. So isn't there any better way to interpret the clinical result? So nowadays, we believe that from 2D to 3D and even 3D to 4D would be better. But you see, the simple parameter, in some sense, works better. So this is the one subject. It's very difficult. This is a 3D plot, right? 3D plot of the one subject in 2008, and I skipped the 2009, and this is a 2010. But if you look at this 3D contour from the top, right? From the top. Now it's a 3D. But if you look at from the top, the height of this one just smashed into it. So only 2D left. So that's what we did. If you look at it here, this point is located to here, and this probably here. So this one is the critical fracture load, structural analysis, Berkman rate, geometric analysis, bone mineral density, which is material properties. So if you look from the top, right? So this is what we get. Okay? So you see that this point, if you look at it in the 3D plot, you probably think that the Berkman ratio is a 5.5 and this is a 0.6. But remember, this is in 3D plot. If you look from the top, you see that actually it was, Berkman ratio was about 5. So this one actually going down to this much and 0.55, something like it. And this is 107 subject information. Some has the lower strength, like blue color. Some has the higher strength. Okay? So this one is actually in the 2D plot, data overlapped of the 107 subject in 2008, 2009, and 2010. So by looking at these color changes, right, with the same subject, you see some of them, blue color, which is a weak subject, let's say the weak patient, right? The number of weak patients is increasing, right? But those who have the high von Mises stresses, see, they're also increasing in 2 years' time. So that's how we interpret this data. So this is the result 2008, 2009, 2010 of all those subjects. You see, y-axis is the femoral neck, bone mineral density, material properties. X-axis is the Buckling ratio. Buckling ratio, if you understand the thin wall pipe theory, then the high Buckling ratio, low BMD area. So we probably want the Buckling ratio is getting lower. The higher the Buckling ratio means that it works like the Starbucks straw. It's easy to buckle. Okay? It's not oil buckling. Okay? This is local buckling we're talking. So 2008, as compared to 2010, you see some of those subjects who has the high femoral neck BMD, who has the low Buckling ratio. These are the group who took the anti-resorptive medicine, which is a bisphosphonate. There are two types of the osteoporotic medicine. So they took one kind of medicine over 3 years. You see some of this area in the second quadrant is bone is getting stronger. Fourth quadrant, bone is getting weaker. Okay? So there are some subject. If you look at the location or area of the blue color, as we are getting old, 2008 versus 2010, you see the more people, actually the area of this bone mineral density area is getting bigger, means that they are getting older. So even though they are taking medicine, their bone mineral density is decreasing. So medicine doesn't work. So natural aging actually override the effect of the medicine. But those who are located in the second quadrant, their bone mineral stress is getting higher and higher. So these are the subjects who really, their bone is getting stronger as compared to 2008. Okay? So up to now, we can only get the bone mineral density from the clinic, right? Material properties. But we can actually see the geometric changes in the Buckling ratio, which is represented in the x-axis, as well as the color changes, which is the structural properties. So here, what we've been talking is now the current diagnosis is oversimplified, which is a single predictor, and also it's averaged. And also there's a substitute for geometry and strength. So now we need a more rigorous diagnosis. Not only the bone mineral density, we can get the hip structural analysis, geometric analysis, which can measure the Buckling ratio, as well as the finite element. And instead of average, you see that the femoral neck, you can consider it as a donut. Do you consider all of this femoral neck in one rigid body, or there's just like a crack on your front window, right? Even though there's a small crack, it can create it. It has energy, like a stress concentration. It can propagate to the crack or fracture. So instead of all average value, which is current standard, we have to see the localized changes. There are certain area of our femur which is much weaker than the other areas. Okay? And also, we have to include this as geometry and strength. So I got this paper actually the other day. This is a paper just published, in bone. They call the focal osteoporosis. Now, this is to me, this is quite interesting. Instead of considering the femur as a whole, okay, just remember, if you take the X-ray, right, you have a 3D structure, but X-ray in the film is just a 2D, right? So that's what they're doing these days. But they consider the importance of localized weakness. Okay, they call the word the focal osteoporosis, which means that the focal osteoporosis defect plays the important role determining the fracture risk. So, I mean, this is the typical, there are hip fractures, and then they have the cortical bone defect. So they compare the 70 fractured femur versus 70 healthy femur. So if you're comparing those two, the differences shows on this color. You see that this top area is called the superior area. Superior femoral neck, and that even trabecular bone. So, and also this is the backside of the femoral head is a weak point, which shows the big differences. So this graph, actually this figure tells that the elder bone, let's say we have 1, 2, 3, 4, 5 regions of this femur. It's not just 1, 2, 3, 4, 5 femur, 5 area reduce the strength. The other area, like a cortical head or something, or even in the lesser trochanter area, there isn't any changes. There is no difference between fractured bone and unfractured healthy bone. There are only certain area shows the differences. So with that idea, I mean, I remember, I know Jonathan Reeve, and we've been talking about this a few years ago, and then he recently successfully published a paper. And we called, what I presented is instead of, I call the focal, I use the local. I use the word local, which is the region-specific areas. So we look at the local buckling ratio, which is a very crude method, and then predicted the fracture load, and we call the local osteoporosis. I mean, we published it a few years ago. So the second part is that, as I said, we want to see the efficacy of drugs. A lot of pharmaceutical company, they advertise that, okay, this subject, like 100 subject or 50 female subject, they take this medicine, their medicine, new medicine. They even get injection. Previously, they had to take every single day. Also, they have to upright because of the acid reflections. And nowadays, once a month, or now in the injection, like even once a year, osteoporotic medicine. And they always advertise that, okay, this person, bone mineral density has increased after they take this medicine. So this bone is getting stronger. But as I said, we say that, well, that's not really true. So we took a little bit challenging work. I mean, this eventuronate, rigidoronate, relaxofene is actually just a medicine, okay? So anti-resorptive medicine, which stopped the bone remodeling. So we look at the quantitative manner or qualitative manner. You see, what is the percentage improvement in strength? But also, we were interested in is that the location, where? Where does the bone resorption or opposition happens, okay? So as I said, in the proximal femur, you cannot just assume that medicine affect all the femur with the same manner. They work in certain areas, they don't work in certain areas. Okay? So we were interested in the location, and also we were interested in how long would it take. Okay? So pharmaceutical company, they don't like me because I said their medicine is not really working. I mean, if you look at it here, I mean, I skipped the experimental side, but we look at the femur based on the adequate, inadequate, and indefinite group. So adequate means that bone is actually getting stronger. Inadequate means that bone is getting weaker. And this one is, nothing have changed. But all of these people, they took medicine from their company. Okay, so we used the same subject. So they always complain, they always said, okay, these are their femoral neck BMD or their overall BMD, bone mineral density, has increased. So according to the company's point of view, all of these subjects are supposed to help their sellings, right? Because bone mineral density is increasing. Or it doesn't really losing anymore. But we just, out of those subject, patient, that they are advertising, we actually divide. We look at it a little bit more factors. And we could successfully divide into 3 groups. Okay? You see that those groups who increase their critical fracture load, decrease and not much changes. But if you look at it in the overall buckling ratio, which average the value of this femoral neck, there's not much differences. See, these are A, B, 1, 2, 3 groups. they definitely have differences in the critical fracture load point of view. But overall buckling load doesn't work. Femoral neck BMD, no differences. Now the current gold standard is the femoral neck BMD, which doesn't show any differences. But out of this one group, according to BMD, we could divide into the three groups. If you look at the subject 1 and subject 2 or subject 5, right? But however, if you look at it here, overall buckling ratio doesn't change, okay? But critical fracture load shows the huge differences, okay? So here, what I'm trying to show you is that there are certain regions, critical region concealed by averaging the local value. So we are using the averaged value. So it is not, it's not important. If you look at the front window of your car, right? If there's a small crack happens, right? You have to consider that as a broken one. So because it has a much higher chance of fracture, right? So this is the graph which we've been published a few years ago. And I had a long debate with the medical doctors from pharmaceutical companies. So we again have the adequate group, which works, which means that the bone is getting really stronger according to our point of view. This is 2008, 2009, I skip it, and 2010. So this group, increasing the critical fracture load, these are 2008, 2009. Look at this buckling ratio, and this is a profile angle, 0, 30. So this is 0. So this is superior, inferior, this is anterior region. 0, 30, 60, 90. So that's what it means, 0, 30, 60, 90, up to 330, okay? So if you look at this picture, you see those who increase the critical fracture load, you see that the buckling ratio, right? There isn't that much changes, right? However, if you look at inadequate group, which is a weakening group, in 2008, if you look at in the 30 degrees, which is the weakest point, which is superior anterior region, this region is kind of weak. Even though you look at it, the cortical thickness, right? You see that this is a kind of thinner as compared to this side. There's no fracture happening usually on this side because it's quite thick. In 2008, you see in the 30 degrees, buckling ratio is about 7, right? Now, in 2010, this group is getting up to 8 or over 8. Means that this bone is actually getting weaker in terms of geometric analysis. This one, actually, you see that there's not much differences in definite group. Strange, but out of those who increase the bone mineral density over 3 years, they got about 30%. Okay? So we are actually still chasing this group to see whether my hypothesis is correct or not. So what I'm expecting is that there will be more fracture happens in this group and this group. There's much less fracture happens in this group. Okay? So very simple. So this is basically the same. This is again the same as the Jonathan Reeves group, just published it. If you look at it, the superior anterior region, which is a superior anterior region, okay, and also inferior posterior region, okay, inferior posterior region. Superior, so this is a 30 and 180 to 210. So 30 degree and 180 to 200, these two regions, which is in accordance with our data. And they show that when this color is just to show the differences between normal and like a healthy and osteoporotic fractured group. So we can see that the location we predicted using very simple buckling ratio analysis actually in accordance with the finite element analysis from other groups. And also, it is true that the surgeons already know the femoral neck is weaker in this region as well as in this region. It's not because of the material property. It's just because of the way we are walking and the way we are falling. We don't fall on this way, right? We don't fall anteriorly. We can usually fall on the posterior region. And also, it was a little bit not just happening on the sagittal plane, but also on the frontal plane. So honestly, we are falling like this way. We don't really fall this way either. So because of the falling pattern of human, that's why these two reasons are weaker as compared to other reasons. So the summary, as I said, the current gold standard, bone mineral density, and also the Buckling ratio had a significant linear and increasing relationship. Okay, so what we have found is actually in accordance with the BMD at the beginning. And FCR, critical fracture load, and the BMD also shows the positive relations at the beginning. And so if I combine these first two, high critical fracture load values were found at the region containing high BMD and the low Buckling ratio. Yes, up to this much, yes, we could understand. But as I said, the critical local Buckling values were consistent with the FE, and then lower and higher range of local Buckling ratio, okay, were found on the adequate and inadequate drug treatment group respectively. So what this means is that even though bone mineral density is increasing, we have a technology which can differentiate those groups. Okay, so increasing bone mineral density doesn't mean that your bone is getting stronger, vice versa. Even though your bone mineral density is decreasing, which all of us will happen sooner or later, okay, that doesn't mean that we'll have a fracture. So we have to use the more rigorous technology to understand or predict or diagnose the femoral neck fractures. So that's the first part of my presentation. The second one is actually quite short. So another thing is that the experimental approaches. Now I've been complaining or discussing the high risk of relying on the bone mineral density only. Then what about in the experimental wise? Do we have any evidence to support our hypothesis that bone mineral density alone is not enough? That's our hypothesis. So objective is to examine the relationship between changes in the viscoelastic properties, right, which is modulus hardness, viscosity eta, and tangent delta associated with the overrectomized and the treated rat groups. So this is a 5 group. Sham is we just open up the belly of the rat and then just close it. Overrectomized, actually we remove the womb of a female rat and we accelerate the osteoporosis. Parathyroid hormone, which is anabolic treatment, increasing bone remodeling. So we get more bone, we lose more bone. Okay, as I said, during the class, but see, bone remodeling is always like a two wheel of a bicycle. You get more bone, you lose more bone. Okay, you get more bone, you lose more bone. Okay, but when you're in the 20s, right, you get more, you lose slowly. That's why your bone is getting bigger and higher. In some of later, you will have the same circle, just like a bicycle, that maintain. But when you're getting older, over 30s, you're losing more, you're making much less. That's how the osteoporosis happened to your bone. So this parathyroid hormone, PTH from 1 to 34, what they do is that you just boost up, like an energy drink. Okay, we can lose more, but we get more. Ibandronate is the one kind of anti-resorptive bisphosphonate. This one, what they do is basically they just stop everything. Okay, we don't lose more, but we don't get more. So there are 2 different types of the medicine. Or, I'll show you later, but we, in our lab, somehow we successfully combine those 2 together. Okay, so we stop the resorption, but somehow we increase the bone formation. Okay, so with this, we use nanoindentation and also the dynamic mechanical analyzer and modulus hardness, viscosity, and even viscoelastic property damping. Tangent delta, we could get it. So this is viscoelastic load bearing. So y-axis can be either stress or strain, x is a time or frequency. You see that the input and output, there's a time delay, which is a phase delay represented by delta. And also the amplitude decrease, which is the energy absorption happenings. So tangent delta is defined by the loss modulus over storage modulus. Okay, so it's basically how much, so that's why we call the mechanical damping. So what we did, this is our sample rat, right? Nice looking. I mean, it's okay in the normal day, but when we inject or we do something, they can bite. So after we raise them, we feed them, we provide everything, and then we kill them. We get the bone. So this is in the middle of the diaphysis. Then we cut the sample, prepared like this, and we use a dynamic mechanical analyzer. Remember the previous figure, like a loading, unloading, sinusoidal curve? So that's what this machine can do. Hope I can play this. You see that the loading, unloading, loading, bending, tension, compression, it's dynamic loading. So that's how we get. So what we get from the result by using this DMA is that if you look at y-axis, this is the modulus in gigapascal. X is a tangent delta, mechanical damping. So if you look at the structural metal, like a steel, like a brass or aluminum, they usually have a high modulus, but their damping is usually low. We know that, right? But if you look at the rubbery material, like rubber or even leather, they usually have a low modulus, but they have the higher damping, right? Our bone somehow located in the moderate modulus as well as their damping. So if this normal bone, if the osteoporosis happen, it's not just the modulus problem, but also the damping problems. Okay, so up to now, so once we have a treatment, okay, we believe that then the modulus is increased. There's many papers, over 1,000 papers, shows that they're osteoporotic bone. We give a medicine, and we tested the modulus, and then, modulus is increased. But what about the damping? What about the differences in the x-axis? Okay, to get the mechanical damping, or another way is a load-bearing capacity or shock-absorbing capacity. To see it, we have to work onto the viscoelastic property, not just the elastic properties. So another thing is that the nano-indentation, Dr. Oum in the civil engineering MIT have the excellent video on the nano-indentation. So this is always happening. Okay, now it goes. So for those who don't know what is the nano-indentation, this is very nice and good equipment. So this is a sample surface, and this is a Berkovich tip, right? So what you do is that just indenting. So you're loading, indenting, right? And holding and unloading. So this is the very simple, very well-known, typical, rationale of the nano-indentation. So you do this, okay, in the surface, so you indent it. Okay, so you can indent with a different pattern. Okay, you see that? There are many indentations, right? Different patterns. Nowadays, by using the fingernail, now I know that by looking at the eye scanning, people can see or tell whether you have a diabetes or no, right? That was very popular 4 or 5 years ago. Nowadays, if you cut your fingernail by using nano-indentation, people can tell whether you have osteoporosis or no, right? So again, in the quasi-static loading, so you need the loading to get the stiffness and unloading to get the hardness. Nowadays, the continuous stiffness measurement, while you're increasing load in the load displacement curve, it's not just simply loading. Excuse me. What you do is that while the overall load increase, you got the loading, unloading. So loading, unloading, loading, unloading, loading, unloading. Okay, so machines are getting smarter. So that's how we get the, even creep, we can get it. Okay, so that's how we got the modulus and the hardness values. So by using this previous DMA and nano-indentation, So y-axis is the viscosity eta. X-axis is the cortical modulus, okay? Young's modulus of the cortical bone. So this is the sham bone. Sham is actually, as I said, just a pretending. We do the over-rectomizing. So these are the sample values. Shows that we just consider this as the normal bone. Those who have osteoporosis, then they just from this curve to here, they just not only they lose the cortical modulus, but also they lose the viscosity value. With the parathyroid hormone or with the ibandronate group, okay, their value is actually here. Means that their cortical modulus, okay, you see that the first one located from here to this much, right? This one, black color, which is this one, original. Osteoporotic, drug-treated, monotherapy, which means that either parathyroid hormone or bisphosphonate. So that they actually regain a cortical modulus, but they don't really regain the viscosity value. But if we combine those two medicines together, then, as you can see, these blue colors. So we got the viscosity almost the same as the normal bone, but actually the cortical modulus, in terms of the delta X, actually we can regain the more cortical modulus as compared to the original bones also. So this graph actually tells you that we can get the viscoelastic material property by using certain techniques. So up to now, the only availability was the cortical modulus. Of course, we can use the morphological analysis using the peripheral QCT. Okay, we kill the rats, and then we put her bones in here, and then we get the even micro-CT analysis. So these are the simple animation. Shows the micro-CT. This is the sham bone. This is a sham bone, original bone. This is cortical and the trabecular. So once you over-rectomize the rat, you see that trabecular bone is almost gone, right? Which we already know. If we treat it with the parathyroid hormone, this much, we treat it with the ibandronate, which is anti-bisphosphonate, this is what happens. So if I combined it, so this is very well-known synergistic effect. So if you do the monotherapy, either PTH or bisphosphonate, okay, there are more than thousands of papers showing that this one is better and this one is better. But there is a very well-known paper, Daniel Black, which is in the New England Journal of Medicine. As you know, the impact factor is quite high, over 60s. What he did, is that this is a parathyroid hormone, PTH, and alendronate, which is a bisphosphonate. And also, he combined those medicines together. So as I said, so either one, this way, A type or B type. And then he did testing to human, combined these two drugs together. So this is a combined group. And his conclusion is that there's no synergistic effect or additive effect. So it doesn't work. That's what he said. He's from San Francisco. On the other hand, Phyllis Kosman, she's in New York on the East Coast. She shows that, well, there is a synergistic effect by combining type A and type B. So we were wondering, how come? One person in the West Coast, they said no. East Coast, they say yes. I was in Singapore. I didn't belong anywhere. So we were wondering, actually, we got the synergistic effect. There are 7 papers. We look at the 7 papers, each of them, and we analyze it and see what would be the difference. PTH and bisphosphonate, the ratio was 1 to 100. This one, Phyllis Kosman, 1 to 0.3. So it was a huge difference. So we were thinking that probably the ratio of taking it. I don't know the pharmaceutical or biological effect of it, but we are engineers, starting from very simple things. See that maybe the ratio. Then somehow we choose, let me be honest with you, we choose 1 to 0.7, okay? Because it's a rat. Of course, we try the several trial and error. And then of course, we did the mechanical testing with the 3-point bending. We modified we made our own jig, custom made for the rat tibia, and then we do the micro-CT and PQ-CT analysis. As you can see, this is a sham, ovarectomy, PTH, eventuronate, and combining those two together. So this is cross-sectional view. So conclusion, or our result, what our result shows that over 12 weeks, okay, with the type A medicine, type B medicine, this is A and B, really it works by using micro-CT or PQ-CT. So this is, and also this is, what about the BMD? So this is OVX group, sham, PTH, eventuronate combined group. So if you look at in the one slide together, osteoporosis, normal bone, treatment A, treatment B, and combining it together. You see, this is the sham, normal bone, and this one looks very similar. So from the PQ-CT analysis, in terms of the bone mineral density, we have shown that the combined therapy or shows some synergistic effect. And also, of course, we have used the micro-CT, and we showed that what happened to the corticotrabecular structures. There are certain changes in the cortical thickness, okay? And all of those shows that it shows the synergistic effect, but it's not really that great, okay? A has an advantage and disadvantage. B has an advantage and disadvantage. What we want is just advantage, and combine together. But that probably works in the movie, but in reality, especially with the biological system at rat, it didn't work that well. Remember, you guys already saw the SEM, right? Scanning electron microscope. So we had that also. So this is OVX bone, osteoporotic bone, sham bone, PTH or eventuronate, and this is combined bone. By looking at, just superficial, by looking at the bone itself, we probably show that combining, it looks much denser as compared to the other treatment, right? So we can actually add this to our paper because of the density. By looking at this, the density-wise, probably this combined treatment works. The last thing we were interested in is that the vibration, I'm not sure in Japan, but in Korea, you go to the public bathroom, they have the whole body vibration machine. So there's a very well-known paper published in Nature that what he used is the lamp. So overrectomized the whole body vibration with the animals, and actually he showed that the bone mineral density has increased by using whole body vibration. So that's why in Korea we have lots of whole body vibration machine, even in our school gym. So we were wondering that, is it really working to a small animal? So we purchased the whole body machine, the vibration machine, and then we tested it. But unfortunately, there isn't any big difference in terms, by using the whole body vibrations. Okay, this is sham, OVX, and vibrations, and after 20 weeks, it doesn't really show the differences. We follow the protocol. We contact the author of the Nature papers, and we still couldn't find the really interesting result. So this is the summary. The combined administrations, offers an added advantage in preserving both viscosity, eta, and the loss tangent of the bone, which is the viscoelastic properties. And eta and tangenta could possibly be important parameters in bone strength prediction, hence the fracture risk association with osteoporosis, and the mechanical testings are needed. When I present this, I always get questions, then can we get the viscoelastic property from human? Okay, unfortunately, not yet. We cannot really apply to human beings yet. But I just showed, again, the important thing is that the first part is that I complain or I appeal that bone mineral density is not enough. Second part is that also the elastic property is not enough. So what I'm saying is that we need something new, or we need another approach, novel approach to predict or to get the properties of our bone. That's what I'm claiming. So this is what I like. I always use this when I present it in the medical doctors. He said, don't do this, don't do this, don't do this, don't do this, don't do this. Then you'll be safe. You're not going to have a fracture. Okay? So how many don't? I don't know. But if don't, they probably say don't die. So what I always claiming is that the increased drug or improved diagnosis. This part, there's nothing much we can do. Okay? But improving diagnosis using our technology, especially we are engineers, right? We can definitely predict the accuracy of predicting osteoporotic or even obesity or gender-specific fracture rate. So this is take-home message. Bone quality, some of you probably heard, this is my last slide. Bone quality, okay, the definition of bone quality is actually predicting osteoporotic fractures. We can approach like a bone remodeling, balance of formation and resorption. We can work on the cellular level, okay? Or we can use the morphology like a micro CT or PQCT, okay? So using images, we can approach to the bone quality. Or clinical or most common and easiest and cheapest way to approach bone quality is the bone mineral density, okay? But again, we don't have accuracy over 50%, okay, of predicting fracture. So what I'm saying is that not just this. I'm not saying the bone mineral density is useless. This plus alpha, then what would be the alpha? Personally, I believe it's not just the simple elastic properties. There should be a certain way we should approach to a load carrying capacity or shock observing capacity, right? To see the strengths of our bone in detail. So what I'm saying is that the BMD, it can be a geometric analysis or structural analysis or maybe some other newer technologies that we don't understand yet. But what I'm saying is that don't just refrain ourselves. That since BMD is working, we just believe that it is working. We've seen many cases that we believe that was the real theory or real law or rule, but it was always a possibility. There's a slight chance that it's not really true, okay? And the technology achievement or technology development in all areas, okay? So I believe we can apply that to predicting, in our biomedical analysis as well. With that, I want to finish my presentation, and I'll be happy to take any questions. Thank you.
Thank you for the lecture. I'd like to take some questions.
Thank you very much for your informative and inspiring talk. I didn't know about the combined use of two types of drugs, PDH, bisphosphonate. But let me ask two short questions in your numerical part.
Yes.
You analyze using finite element method.
Yes.
And how do you model the trabecular bone part?
Well, there are, I wish I don't get that question.
Because reflecting the BMD and if we can...
No, the result, what I'm just show you here is that we didn't include the trabecular. We
You
just have the
didn't
cortical.
Oh,
because in the strength-wise, there's always debate saying that the trabecular plays a certain role, but it related onto the acceleration of your analysis. So we make these things are quite simple.
May I understand that you, in a sense, neglect the effect of the trabecular bone?
Well, in this specific analysis, but we know that the trabecular bone actually distribute the concentrated loading to overall areas.
Okay. But in modeling the cortical part, we have to give the mechanical properties of the cortical bone.
Yes, yes.
Throughout the 3 years, how can we know the change of the possibility of change of the Young's modulus, for instance, of the cortical bone, if you trace the same patient? Yes, or do you use the BMD?
Well, BMD is one parameter.
Okay.
Okay. The way we do is that it's related to the subject. They're quite old. Okay, so most of them, the way we do that is post-menopause, after 10 years of post-menopause, female only. So we know that there are several papers showing that the actual cortical material properties in this 3 years period after they reach to 60 years, it doesn't really change that
All
much.
right.
A lot of differences happens in the trabecular bone.
Even when the drugs are given to the patient.
Yeah, trabecular,
all
trabecular
right.
structures wise, yeah, it doesn't really shows the
Okay.
differences.
Another question is that your talk today mainly focus on the fracture of the femur neck.
Yes, yes.
And the cause of the fracture, I believe, I understand, was the falling down or slip down.
Yes.
So is your method also applicable to the vertebral or lumbar bone?
Well, in some sense, I mean, we can do it. Of course, I mean, if you understand the how simple boundary condition we have used, right, for the fall, the bending on the spine, vertebral fracture is actually usually happens when you lift up something, right? Or when you lift up something, or when you lift up your leg. So it's actually simple, probably would be more simple cases of a bending side. I mean, so if we have but the thing is that over there, the ligament or muscle analysis, we cannot just simply bend 3 functional spine unit, right? So it would be more, I know it is more complicated to have the boundary conditions, but actual loading, fracture loading, like a slippery in the femur, it can be just a simple bending. Yes, I think so.
Thank you very much.
You're welcome. Thank you.
Any other questions?
I want to ask, what's the resolution of the CT images, and what software do you use to do finite element analysis?
Resolution-wise, I don't remember, sorry. What software we use? We have used the Abacus. Yep, we have used the Abacus. And I mean, of course, we got the QCT images, right? I believe we have used the Mimics for the rendering, and then we applied, and then we use the Abacus software. That I don't know. I know.
Okay, thank you.
Any other questions? Okay, may I briefly ask a question? And I'm interested in the BR, is a buckling what ratio?
Buckling ratio, yes.
Why do you divide R with thickness?
Well,
If R increases, then yeah, it has more it's more resistive against the bending moment, right?
Yeah, in terms of section modulus.
Same
Yes.
for the thickness as well. So
Yeah.
why do you divide R with T?
Why did I divide R with a T? Well, I understand that your point of view in terms of the mechanical engineering. So in the clinical side, what they have used, I mean, it started from the hip structural analysis in the hologic, which is actually selling with the hologic DEXA machine. So my former advisor, Tom Beck, have defined as a buckling ratio as the R over T thickness. But more painful question would be, to me, is that how accurately we can define the T in each ray, right? Because we cannot really use the high resolution images. Okay, so that's actually one of the issue we have. So back to your question, so why have I used it? Actually, that was how we defined it. My advisor defined it as the R over T. Okay, but just understand this as not as the Euler buckling. This is a local buckling. Not just Euler buckling, so it's the local, like just a straw. That's how we use this concept. Okay.
And also talking about the cortical bone and the trabecular bone.
Yes.
You think the determining factor should be the cortical bone?
The way we look at it is that the initiation of the crack, trabecular crack or initiation of the breaking of trabecular bone doesn't really affect the cortical that much. So once the cortical bone outside, the thick bone crack happens, then it can initiate, the energy which can pass through the cortical bone is much higher than the energy that can pass through the trabecular. Trabecular is much weaker, right? If you consider things. So we believe that the initiation of fracture is not starting from trabecular, of course trabecular, but those energy which can reach up to fracturing the trabecular is not really a determinant of fracturing. So the energy, certain threshold which can make the crack or break the cortical bone, then the trabecular doesn't play that role because it's already over the critical limit of the trabecular bone fracture.
Yeah, I understand that. Then, but when you are talking about the bone mineral density,
Yes.
it basically talks about the trabecular bones, right? And
And
does
cortical.
it include the cortical
Yeah,
as well?
it also
so
includes
the
the cortical.
quantify both cortical and trabecular.
No, they
bone.
use the overall values.
So yeah, it's
Because
it's projected.
yeah,
that's
projected.
I
Just
see.
like a CT image.
So it combines both.
Cortical and trabecular.
Okay, all right.
But let me add one thing. There's a software called the trabecular bone score, which I didn't include in here. So trabecular bone score is something between the bone mineral density and FEM. So actually, they look at the location of the hydroxyapatite, even though in the same BMD, bone mineral density, based on the location of the bone cells, trabecular bone score actually shows the differences. So the power of the TBS is that you can get the information from DEXA machine right away. Of course, you have to pay. And also the power of it is that it can provide a new insight. So we may not have to go through this computationally expensive FEM. So TBS is actually good because it can look at the location of the hydroxyapatite. Okay, so we are, even DEXA trying to make the progress in terms of the predicting osteoporotic fractures.
Thank you very much. Any questions? If there's no more, then I'd like to close the lecture. And once again, thank you very much for the lecture and stimulating talk.
Okay,
Thank you very
Thank you very much.